good morning. I can
Good morning, madam.
गुड मॉर्निंग मैम.
चलो गुड मॉर्निंग देखिए अच्छा तो लग रहा है. कल लग रहा था सबको बहुत गुस्सा आ रहा है अटेंडेंस को लेकर. तो जस्ट टू स्पीक अ वर्ड फॉर दैट, अटेंडेंस को लेकर गुस्सा करने वाली कोई बात नहीं है. बिकॉज आई एम सो पेशेंट. प्लीज सम व्हाट पेशेंट. ऐसा होता है केवल एआईसीटी की तरफ से एक सिंगल कोऑर्डिनेटर दिया गया है. आपको अकेले करना है सब कुछ. एवरीथिंग यू हैव टू मैनेज अलोन. So I request again to be a bit patient, and believe me, I am not going to upload the attendance on AICT portal before your approval. That is for sure. Okay, now, oh yes, Dr. Sreenivasa है.
Hello, good morning.
Good morning, sir.
Hello.
Hello, good morning, sir.
Yeah, good morning. Who is speaking?
Sir, this is Abhishek.
I see. Okay.
Yes,
So I'm able
sir.
to connect, just now able to connect to the network. There has been some network issues here. So give me 2 minutes for me to, start the talk.
No,
How many participants do you have? I mean, is there some slight delay? Can I take a few minutes to set up my...
yes, sir. You can set up. There are around 53 participants now.
Okay. Am I clearly visible?
Yes, sir.
No issues with video and audio?
No, sir. It's clear.
Okay, very good. That's very good. So let me just then set up my presentation and then we can start off.
I'm also back. So the network is fine at your place now.
No, I have shifted to my office and so there is a better connectivity for me now. So I will temporarily, kind of, okay. So I think I have to, it takes a few minutes for me to set up my presentation because I just now came to my room.
Please do.
Sarika,
Yes, sir.
sir, do you want to do any introduction in between? I mean, I'm ready to kind of start off. If you want to do a little bit of 1 minute or 2 minutes introduction, and then I can start my presentation. I'm ready.
Definitely, sir. So, dear participants, I'd like to introduce Dr. Sreenivasa with you. He has completed his BTech in ECE from Sri Venkateswara University College of Engineering, Tirupati, Andhra Pradesh. He has then earned a master's degree and PhD from the Department of Computer Science and Automation, Indian Institute of Science, Bangalore, for the School of Automation at that time. After a brief stint as a researcher in the Center for Development of Applied Computing, that is CTEC Bangalore, he joined the Department of Computer Science and Engineering, IIT Madras, as a member of the faculty in the year 1993. He is currently a professor in the same department. He was also the head of the Department of CSC, IITM for a 3-year term, 2013 to 2015. Whose current research interests are so much for being with us. And on this platform, I like you to excuse me for that. Even official, I wrongly said your affiliation as IIT Madras. Participant name is IIT Madras.
Yeah. Okay. Thank you, Dr. Sarika.
Yeah. Yes, sir.
Yeah. Are you able to see my presentation now?
Yeah, it is there, sir.
Ontology is for
Program analysis.
yeah, program analysis. This slide is there. So okay. So I think I can get started off. There will be some background noise. You'll have to bear with that because there is some construction going on in my department. I will try to be as loud as possible. But if you have any problems, you send me a chat message. I am able to see the chat message also. Okay, is that all right?
So for the time being, we can see that background noise is there, but it is very much manageable because you are more audible than the background noise.
Okay.
It's fine with us for the time being.
Yeah, yeah. Okay, so let me go ahead. Let me start the talk now. So we have, thank you, Dr. Sarika, for kind of inviting me to take part in this faculty development program. So I am going to talk on an interesting topic called the ontologies for program analysis. This talk is on the work of my PhD student Dilip, and he is jointly guided by myself and Dr. Rupesh Nasre, my colleague in IITM here. Okay, so so to kind of give you a little bit of history about this kind of work, you know, I actually would like some of you to kind of you know, turn on your videos so that I'll be able to see what if whether some people are listening and things like that, right? So I will encourage some of you to kind of switch on your videos. I'm able to see some of your videos here. So don't worry that I'm actually able to see both my slides as well as your videos and the chat messages. Don't worry about that. I'm kind of a little bit experienced now with online teaching. So a few of you, if you can turn on your videos, it will be good because I'll be able to see your faces while I'm talking. Yeah. Thank you, Praveen Kumar and Mrs. Prasanti for turning on your videos.
Thank you, sir. We are happy, sir. See you, sir.
Yeah, it's nice to have a face-to-face connect when we are talking about it.
Yeah, I understood, sir.
Yeah. So yeah. Okay. So let me tell you a little bit of now that I'm actually talking to the faculty. Let me tell you a little bit of history about this work also, in the sense that, you know, ontologies itself is a new topic, and you know, so when you start working on ontologies, we find that we need to have a lot of, you know, domain knowledge in order to capture the knowledge of and then kind of represent that in an ontology. Okay, so that being the case, you know, I had experience of working with, for example, mechanical engineering domain with Ford Motor Company. And then I had a student from VSSC Trivandrum who was working in space applications. So like that, I have varied experiences in, you know, trying to do that in various domains. Then at certain point of time, I got this idea that we have our own computer science field where, you know, software engineering and then writing programs and then, you know, figuring out whether the programs are correct or not and things like that. That's a big domain by itself. So why don't we start applying ontologies to this particular domain itself is one of the ideas that that I was toying around with and then I kind of mentioned it to many of my graduate students around 2015, 2014, like that, almost 5 years back. And then suddenly it was one of my student, Dilip, actually has has kind of picked it up. And just before that in 2016, there has been a paper which I will talk about in a little bit more later, in the area of program analysis. In the area of program analysis, there has been a paper which applies ontologies for analyzing programs. So in fact, that's what I'm going to be talking about elaborately. So this area is kind of evolving research area. Right now, the international, the ICSC conference also has just started a knowledge grasp for software engineering kind of a workshop in just 2020. And it's kind of very nascent area, and so actually offers us a lot of opportunities. Okay, so with that, so let's get an idea of what exactly is program analysis. So because I'm talking about two different, right now you have some idea about what ontologies are because you have been attending a few lectures from yesterday. I mean, sorry, for a few days now. Let's see what is program analysis actually. So program analysis is this area which is very tightly connected to compilers, tightly connected to compilers. And here we want to find certain properties of programs. Okay, so that means various things, like for example, we want to figure out what is the state information about variables. So what is that we can know at the compile time. So remember that we are not going to execute the program. We are only looking at the program at compile time. So at the compile time, what is it that we can figure out about a particular variable? What are the possible values it has, or what range of values it has, and various things like that. And also, for example, where does this the definition of the declaration of the variable reach? What is it's called reaching these things. So for example, I will give you an example, interesting example here. Suppose you have a global variable in a C program. You declared it as a global variable. We normally discourage people using from global variables. So let's say you have also, let's say the X is a variable. You also kind of defined this, intended to use this as a local variable in your function. In some function, you try to use this as a local variable X. Now, but only problem is that in this local function, you forgot to define declare X. But since global variable X has a scope of the entire program, so this X is valid, and at compile time it didn't give any problem. So when you execute it, actually, this X would be treated as global variable, and then unnecessary consequences will happen because of that. Okay, so there may be some errors that will, but in your mind you're thinking that X is a local variable, and you're going kind of using that and things like that. So there is a difference between what you're thinking and what the compiler has, information that the compiler has. So this will obviously lead to problems, right? So these kind of, so you would like to know if there is a variable, where are all it is reaching. That means in the program, what are the various program points or statements where it is valid or applicable, things like that. And then you also do what is called points to analysis, in the sense that if you have pointers, you would like to figure out what are all the various, what pointer is pointing to what other thing, etc. Right? So these are the various kinds of things that you will like to figure out about a program at compile time. So this is what is called static analysis. We focus on static analysis because we are not executing the program at this point of time. We are only compiling the program. So at the compiler time, at the compile time, what is it that information that we can figure out from the program? So that kind of thing is what is called this program analysis area, and it has certain of the compilers have these additional program analysis packages that we can make use of. So it's kind of used in many areas like code optimization, register allocation, trying to parallelize the code, and then also trying to find out bugs in the program and things like that. So these are the various things that do happen in program analysis. So when in 2016, there has been a paper about one of the first papers about trying to use ontologies for program analysis. But before that, what was there is that there used to be what is called an imperative approach for specifying as to what is to be done in a program analysis. See, so you have programs and you want to now analyze those programs. So somebody has to kind of say as to what is expected out of this analysis, right? So that's what we call it as analysis specification. So how do I do this analysis specification? So one of these approaches that was tried first was the imperative specification. That means you use the same kind of languages, like for example, if you focus now on C is an imperative language. In a similar way, you also use either C itself or something else, and then write your specification as to what should be done, what analysis needs to be done. So that means you basically write another program to analyze the target program. So there is a target program and you want to analyze that, then you'll have to write a program to analyze. So so there are these infrastructures like Clang and Rose. These are compiler infrastructures that offer these application program interfaces, using which people can write programs and then collect information about some other program, the target program. So the program that we're analyzing, we'll call it as a target program. Okay. So so this was tried. Actually, this is even now it's happening, because these Clang and Rose are popular compiler infrastructures. But the problem with this approach is that it is very, very tied, very closely connected with the compiler infrastructure. You have to learn that compiler infrastructure fully, and then learn the API and the way they represent the program internally, and each compiler represents the information about a program in its own way, right? So how does it represent, and all kinds of things you'll have to learn, and then make use of these APIs and then write a program which will analyze the target program. So thousands of lines of codes sometimes will have to be written in order to analyze other programs, okay, the target programs. So obviously this will also lead to a lot of maintenance issues, because when you write programs, then there's always bugs, and if you're trying to find out bug in a target program and then you put a bug in your own program that is analyzing, that's even more difficult. The order of the second level bug has come into picture, right? So all these problems will come into picture. I still request some of you to turn on your video so that I can see. I can right now only see Mr. Praveen Kumar and Dr. Sarika, of course. And then there was a transition. There is a thinking that why don't we go for what is called a declarative specification for this program analysis. So as you know, in declarative style, say for example, SQL is a declarative language, right? So in declarative style of specification, we would like to kind of specify as to what is it that we require, and then let the system, the framework that we are using, kind of figure out how to exactly get that information. So there have been some very interesting systems that offer this alternative of declarative specification. But the situation was in such a way that there were a lot of issues with this whole approaches. Okay. So even with the declarative approach, there have been there are a lot of issues. one of the issues, let me list out some of the issues. They're all listed here in the slide. So all of you able to see the slides and all that? So no problem. With my voice, is there any problem? Of course, sorry for the background noise. I can't have much control on that because this construction is going on. Yeah.
No, it's fine, sir. It's visible, sir.
Very good. Very good. Okay.
Yes, the participants to please switch from the video if possible because it maintains gives motivation to the speaker also.
Yeah.
And it is
Yeah.
also
Just a few of you. I mean, a couple of you can switch on the videos.
Sir, could you shed a light on the applications of this one, sir? How this is going to be useful?
Yeah. We're going to talk about it. Yeah. I'm going to.
Sure, sir.
Yeah. So now, I was trying to tell you some drawbacks of the declarative specifications. In the program analysis, it is such a way that that there is no kind of a common standard as to how to specify this analysis. Okay, and then each of these compiler infrastructures were using their own internal representations for programs as well as the results of this analysis. So if under these circumstances, it kind of becomes very difficult for for us to take one analysis, okay, and then kind of write another analysis that makes use of the results of the previous analysis. Okay, so so that kind of thing, integrating the analysis was becoming very difficult. So and also these infrastructures, these frameworks were such that it is not possible for us to kind of add any additional knowledge from the outside world. Like, for example, I have some knowledge about how a set of functions are going to be used in a things like that, or the hardware architecture on which the program is running. Now, these kind of additional information, it's not possible for us to kind of add it, because each of them has their own ways of representing the information. Now, it is at this stage, the question that pops up is that, can ontologies provide a solution to all these drawbacks? So, okay. So, this is the question that we're dealing with in this talk. So, in the year 2016, and one of the first papers that addressed this issue using ontology-based framework appeared in the European Conference on Object-Oriented Programming. ECOOP is a top-notch conference in that area, and there's a Chinese group of researchers who proposed a system called PATO, Program Analysis Through Ontologies. Okay, so what they have done was saying that focus on C programs, and say that, okay, our domain is C programs. I'm going to represent all the knowledge of a particular C program, the knowledge about a C program, knowledge about C in general, and knowledge about a particular C program. I'm going to represent this whole thing as a knowledge base. So that kind of so it's the first application. So I'm going to elaborate on that. The next one in immediate following year was this code ontology. It is it works. It tries to do similar things as PATO was doing for C programs. It is going to do for Java programs. And okay. So it is around this year when I came to know about this paper, 2016. And by the time actually I was teaching, a course on ontologies and all that, and my research scholar also joined in, I think, 2015, 2014 or something like that. Then I was then motivating my students, saying that why don't we apply ontologies for program analysis? Because first thing is, when you want to do any research work in ontologies, you should first know about ontology frameworks. Then you should also have in-depth knowledge about the domain on which you are trying to apply the ontologies. So these two things are very important. So where we are teaching a course on ontology and we have a good grip on semantic web technologies and all that, when it comes to domain, we are dependent on other people. Like, for example, when we did a project work with Ford, they were, you will be actually surprised to know that they were actually applying ontologies in the manufacturing processes. Okay, and we had no idea. I mean, it was very difficult for us to kind of understand their concerns in the manufacturing area. Okay, so here is a good opportunity for us because the programs we know, and then the ontology technology we know. Then let's work on this. So that's the kind of motivation that we had, and then we worked on this, and we are continuing to work on this. Dilip is yet to submit his thesis. So let me give you some highlights about this work. So this picture in some sense, offers you an overview of how to use ontologies for program analysis. So let's look at various components of this picture. So this figure is from actually that paper, ECOOP 2016 paper. So here is the original program or the target program. Okay, and then so there is an ontology. So how they look at it is somehow we will be able to construct an ontology-based knowledge base about a program, and then after having done that, there will be utilization of that knowledge. So first there is a knowledge acquisition part, and there is a knowledge utilization part. So in the knowledge acquisition part, so the idea was that we will use the target program that is going to be analyzed and do a ontology translation and translate that entire thing into the ontology kind of framework. Then we will also do something about the library functions, and then extract knowledge about library functions, extract knowledge about other aspects that affect the program, like hardware and any other domain knowledge that we may have about the program. So collect all this stuff and then set up a knowledge base. Once we have that kind of knowledge base, then we can analyze the program and write programs, write software that actually analyzes these target programs. So the target program is now represented as a knowledge base. So this was the overall idea that they were trying to utilize, and so it is in this context that what they have done was in the ECOOP paper itself. What they have done, even though they laid out this kind of a grand plan, what they did was to actually propose an ontology translator and represent C programs with the help of what is called a C ontology. Okay, so I'm going to talk about that in the next slide. So the C ontology was proposed by these people. So basically, they were trying to establish this principle that programs can themselves be represented as knowledge bases. Okay, programs can themselves be represented as knowledge bases. So now you have been actually listening to various talks about the knowledge bases and how things are set up and all that. So you know that by now you would have heard about the requirement for having what is called concepts of the domain, and then what are called various properties or binary relations in the domain, etc. All of those things have to be set up. So what these people have done is to take the ANSI terms and convert many of them into concepts. Okay, and then so then they developed a C ontology. So the ontology consists of close to 178 concepts and 68 properties. It's a huge ontology. Okay, and the ontology file is available here. For example, in the Pato Rose, they in fact have actually recently even shifted it to Clang compiler infrastructure. C.owl file is available here. You can download and then put it in Protege and things like that, and kind of study that. So it has 178 concepts and 68 properties. So these concepts and properties, give us a generic framework. You would have heard about the term called T-box in the last few classes, last few sessions. So it kind of gives the T-box terms using which we can actually represent the actual C program as an A box. You also heard about A box. A box is the actually assertional box. That means any particular situation can be represented in A box, whereas the generic schema like knowledge is represented in T box. So what these people have done was to kind of lay down, standardize the various concepts and properties that are required in order to syntactically represent the C program as a knowledge graph, Okay. So so by now actually you also know that yesterday there were sessions on knowledge graph. A knowledge graph is nothing but a set of edges and nodes, like right. So you have a graph like structure. So they were able to represent the C programs like that. Now let me now take you through some of the concepts that they have. So it might look a little bit surprising that you have the usual names and others. So that is nothing surprising because they don't want to introduce new names. They're deriving names from the ANSI C standard. Okay, so they take various nouns that are used in the ANSI C standard and represent them all as classes. So for example, now we have the class of expressions. So all C expressions will fall under this class. Then the class of statements. So all the statements belong to this class. And then you have declarations. So any piece of program that does declaration will be in this class. So now by now you have some idea about a class. That means a class is a set of individual things, right? Or entities. Sorry. So all statements will fall under the statement class. All expressions fall under expression class, like that. So you have. So then type, for example. And then so if you expand declaration, for example, then they have a lot of sub concepts in that. So array declarations and various things like that. So variable declarations, enumerated declarations, function declarations, etc. All of these things are all there. Now, if you focus on expression concept, the expression concept itself has various things like what is the operator and what is operands. So this one actually is capturing all the operators right now here. So what are the binary operators? What are equality operators, etc. So all of these things are available as concepts in the C ontology. Now here is the statement concept. The statement concept has sub concepts like is this statement a basic block or is it a compound statement? Whatever, when compound statements can have function definitions, etc. So if you see iterative statements, then there are what are called do-while statements, and then for statements, while statements, etc. So this you will be able to appreciate because we know that these are all the various things that are available in C programs. Okay. Now, in order to describe these things, we have the necessary concepts in the ontology. Okay. So that is their contribution, and using this ontology, they were able to do certain amount of analysis. For example, they were able to do an analysis called canonical loop analysis. That means they want to figure out whether all the loops are in a particular canonical form or not. Okay, so that analysis can be done once you have the syntactic information about a program as a knowledge graph. Okay, so these are the various properties that are there in the knowledge graph. Okay, so for example, has condition. So has for in it, so that a for loop will have a initiating expression, right? For test, for index expression, like that. There are various properties. That means, so these are the labels on the edges in the knowledge graph. Okay. So whereas what I have shown earlier, these concepts, these are the types of the nodes that are there. Say for example, statement is one type of node. Then if it's a for statement, then that statement has for in it an expression, an initializer expression, right? So these are the labels on the edges of the knowledge graph. Edges on the knowledge graph. Okay, so let me pause here to take some one question, at least one or two questions, so that I'm sure that you're following what I'm saying, because it's very important for me to for you to understand what do I mean by SC ontology before I proceed further. I'll just pause for a minute and then see if you have any questions. If you have any questions. Yeah.
If you have something till now that is going to answer your queries and help you out in developing such applications. So it will be very beneficial for all of us to see how program analysis is done. If you have certain queries, you can always ask him.
Okay, towards the end of the thing, I will be actually open to take some one Dr. Tiwari is asking, is there a need for some upper ontology? I see. Okay. So these upper ontologies are, very generic in nature. They are required in domains where, where we are representing, varied other things like, common sense knowledge and then world knowledge and things like that. But here we are focusing, we are focusing here on knowledge about a C program. So that's why we are able to develop the ontology all by ourselves. No, we don't need other ontologies in order to develop this ontology. And there was a question by one Ms. Archana. How to utilize ontologies for programmers. Yes, I'm going to talk about this in the rest of the talk is about how to utilize ontologies for program analysis. Okay.
In continuation to the previous question, that is it necessary to use upper ontologies and connect them while developing our domain ontology? I want to add one more question to that. If we have some entities like person and organization in our own domain ontology which we are creating, how is it different if we create our own entity or we use the URI of the already existing ontologies? For example, person is there in FOAF, organization is there in Wikipedia. If we commit these entities directly from there, or do we create new? Which one is the better option?
You're asking me a question, Sarika?
Sir, yes, sir.
Okay. Yeah. Okay. So see, if we are building a new ontology, and if some of the concepts that we require are already existing in some other ontologies, then it's advisable that we use those ontologies. Okay. It is advisable. Yeah, it is advisable to use those ontologies as they are. Import those ontologies and use. In this case, of course, since we are developing ontologies for this domain of programming languages, this is a very new thing. So there were not prior ontologies to kind of import, and so we are able to these people able to come up with this C ontology. So actually, when we started working, we are going to now build on top of the C ontology. We are now importing the C ontology and then developing what is called a program analysis ontology. That I will talk about in the later part of the talk. Okay, so let me proceed further now. So now the as I was studying, the knowledge base, the whole situation is that there is going to be a T box or generic knowledge about the domain, and then then this knowledge graph, which is the situationalized or a particular knowledge about a particular program at hand. Okay, a target program. So for that target program, we have to kind of this is where the Pato had a box saying that ontology translator. So that ontology translator, what it was doing was taking the target C program or given C program, and then using compiler infrastructure or the ROS compiler infrastructure actually, and then extracting various pieces and then generating the knowledge graph. Okay, so the individual. Okay, so we call these nodes that are there in the knowledge graph as individuals, because that they represent the actual entities in the target program. So all those things have to be generated by this translator. Now let me show you an example to kind of make this very, very clear. Say for example, here I have a C program on this side. Okay, you're able to see my cursor. On this side there is a C program, and on this side there are triples actually. They look like 3 columns, but each of them is actually, each line is one triple. Each line is a triple. So they don't look at them as columns. They're 3 triples. Say for example, let me take one one thing. Like for example, file line 4 var. C has base type long integer. So you can see for line 4, you can see that there is a variable here which is declared, and the type of that is long integer. So that knowledge that on line 4 certain variable is being declared, so that variable is being abstractly represented like this. So line 4 var, so that is the abstract name for that particular thing. Now that is so that line 4 var is of a variable declaration, and it has a name. C has name, which is size. So size is the name of that variable, and then its type is long integer. So such very detailed pieces of knowledge about the input program are extracted and represented as triples in your knowledge base. Okay. For example, this whole thing is, for example, line 3 to line 18 is a function declaration. So line 3 to 18 is a function declaration. That's what this particular first statement is telling. Like that, we are going to have a very detailed knowledge of this C program that is actually been generated by an ontology translator or ontology extractor, which obviously has to work on some compiler infrastructure, and it will generate these things. So okay, now you can see that. So there is a prefix here. So the C prefix. So C means it represents the namespace of the C ontology. So that means all these terms come from the C ontology. Okay. Whereas file prefix is, these are the names that we give for the individual elements that are present in our C program. Okay. So there's a and then we also use RDF. So RDF is a ontology framework, so which gives a lot of terms to declare to kind of set up ontologies. Okay, so we also use those things. So using a set of concepts that are being declared in the C ontology, we are able to now give very detailed knowledge about the target C program and then represent that as a knowledge graph. Okay, so I hope this point is clear to you now, because we are going to build on top of these things now. Okay. Okay, now let's come to our work. So when the C ontology, we studied this Pato paper in depth, and then we found that this C ontology kind of is doing a lot of interesting work, because it's a big ontology, and it is able to give a syntactic representation of the entire C program and then convert that into a knowledge graph. So that much it was able to do. And they were also able to do, as I was already mentioned, they were able to do canonical loop analysis with the help of this the knowledge graph that they have generated. Okay, so but we found that there's even these Pato people also kind of mentioned in their future work, saying that for real program analysis, we really need a program analysis ontology to be built, and then only we can actually do a lot of interesting works. So that's what we also kind of realized. Then we said that, so unless there is lot more information that we can extract from the C program and then represent that in the knowledge graph, only then we'll be able to do certain kinds of analysis, like for example what are called path sensitive analysis and certain semantic analysis and such things we'll only be able to do if we extract more information, more knowledge from the C program. So that's when we started working on this OPAL framework, ontology-based program analysis framework, which extends our PATO to kind of capture this semantic information. So one of the first things that we capture is this control flow information. And then we also capture what is called static trace of the information. So this whole, and then we proposed what is called a program analysis ontology, which gives a model for storing all this semantic information, and then allows us to kind of reuse this semantic information for various kind of analysis that we do. Okay, so this work actually appeared in the Journal of Software Programming, Software Practice and Experience in this year, SPE. Okay, now let me tell you how to represent control flow graph. So all of you understand what is a control flow graph of a program. So basically, it has so whenever there is a branch statement only, the control flow can either go to the true branch or the false branch and things like that. So in order to represent that, we have defined predicates in the logic language called the if true statement, if false statements. That means if the condition is true, what is the statement that is executed? If the condition is false, what is the statement that is executed? So with the help of these predicates, we're able to represent the control flow also as a graph. And if you represent that as a graph, then we can translate that into triples. Okay. So for example, here you can see that line 4, there's only one branch here. So you can see that there's a if here in line 11. If something, then do this. Otherwise, just jump to line 18. So that is the only thing. So that line is here actually. So that node is here. So otherwise, so from line 4, 5, 6, etc., there is a linear flow. And at line 11, we either go to the true branch, in which case we'll execute 12, 13, 14, 15, 16, 17, 18. Otherwise, in the false, we will just directly jump to 18. So this kind of a control flow that is there. I mean, this of course in this program is a simple one. In general, there can be a large graph which represents the control flow of the whole static, which can be statically figured out of the program. That whole thing can be represented as a graph, and once we represent that as a graph, it's kind of with the help of these predicates, like begin the execution, what is the next statement. So for example, for this, what is the next statement? This is the next statement. For this next statement is this. So for this you can't say what is the next statement. So for this we have if true, if false. Okay. So with the help of these things, we are able to translate this entire thing into triples. Okay. So this is where it begins execution, and for all of them, what is the next statement? And for line 11, this particular thing, what is the if true statement? If it is true, it will go to 12. If it is false, it will go to 18. Like that, we are able to capture the control flow graph also as a knowledge graph. Now, next comes a very, very important component of this whole infrastructure called the static trace of the information. Okay. So static trace of this information. What do we mean by static trace? So first thing is, we are not executing the program. Okay. So we are going through the program, we're compiling. So we want to kind of figure out as to what is the maximum information that we can gather about these variables as in various program paths. So what do we mean by program path? A program path is, okay, if you have a branching statement in the program, then there is a condition there. So depending on whether the condition is true or false, it will take branches. So at that point of time, there's going to be two paths that are going to be generated. So in each of these paths, so certain variables, will have a specific value, or we will know certain, information about the those variables. So we want to represent that entire thing. That's what is called state information. So abstractly speaking, you can represent the state information like this. So it has several components. So you can imagine a tuple like this. So variable ID and a statement, and what is the path through which we reach this particular statement, okay, and our variable, and then what is it that we know about that particular variable. That means is it greater than 0, or is it equal to unknown, or is it positive, less negative, or what exactly is it that we know about that variable? Okay. So to kind of repeat, so here is the variable ID, and this is the statement ID. That means after what statement is this information true? Okay. And then path ID means what is the sequence of conditions using which we have come to this particular statement. Okay, so the sequence of conditions means we still have not executed the program, right? So what we do here is that if you come to a condition, we assume that the condition is true, and then we'll take up one branch, and then the assumed value for the condition will be taken as false, and then you go to another program, another path. So in all these paths, we will gather information as to in this path what will be the variable, in this path what will be the information about that variable. So all of that gets collected in what is called this static trace. Okay, so let me give you an example of that. So for example, for a variable IP1, which is there here in this program, you can probably, did not give you enough time to go through this program itself actually. So if you want to, you can go through this program. So which is saying that there is some input integer IP1, integer IP2, and then there's an integer called C, and then we are opening a file, and then we are scanning, and then getting the values of IP1 and IP2, and we are checking some condition, and then doing something here. We are reassigning the value of C, and then we are computing the size of the file. T is assigned that size, and then we are printing something, and in that printing we are using some variables as the divisor. Okay, there is a reason for this. We will come to that later. Okay, right now the state information for this variable IP1 after the line 15, for example, after this line 15, what will be the variable? So basically, actually, we don't, because it's a variable that is read from input, we really don't know what is its value because we have not yet executed the program. So basically, we represent that. So IP1 after the line 15, and the way you reach line 15 is that this line, the condition in line 11 should be true. Only then we will reach that. And it is equal to unknown because we really don't know anything about that. In a similar way, for variable C, for example, here, C equals 2 here and C equals 4 here, right? So for variable C at line 15, we know that this variable C, which is, after this line 15, which is reached after this condition, its value will be equal to 4. So this is the detailed state information that we are able to, that we can get by doing a static analysis of the program. So now, who is doing the static analysis? That's a very interesting question. Okay, so it is this, the ontology. What is the knowledge to do this static analysis? So these are the questions that I will answer a little later. But right now, let me take any questions if you have about what exactly you mean by static trace. I hope it is clear as to what we understand by a static trace. So now we have two different kinds of knowledge. Apart from the syntactic knowledge that is represented about the program, we have two additional kinds of knowledge. One is this control flow graph knowledge. The other one is the static trace knowledge. So all these knowledge are available for us, and then we can utilize this knowledge. Okay. Here comes our program analysis ontology. So to kind of represent all this knowledge, we need terms again and concepts. So we introduce what is called a program analysis ontology. So actually this ontology is not as big as the C ontology because the number of concepts that you require here are not too many. Actually, there are only limited number of concepts that you will require, but you can represent. Very good. Somebody is asking whether as to how to represent loops in RDF. Okay. I don't know your name. Sorry. Let me try to figure out what is your name. Apurba. Okay, Apurba Pal. Okay. The loop becomes a large kind of a thing only when you execute it. So at the static time, when the analysis, it's just after all a loop So it has a bunch of statements. So in representing a loop is not a big issue. It's a sequence of statements only. Okay, so that's not a major issue actually. In fact, in this we can represent loops. There's not a problem. Especially because we are only representing the program. We are not representing its execution as of now. Okay, that actually also brings into another interesting situation here, but I think I should address it now. That in your static analysis, supposing you encounter a loop, probably that's what the motivation for this question. If you encounter a loop, then how far, how many times will you go through this loop? That's the question, right? That might be an interesting question. So that we will see that there is something called a fixed point for the loop. So if you are entering the loop and then with a certain state information, and then you are exiting the loop with a certain other state information, and then again you are trying to enter the information. Suppose the state information stabilizes at a certain point, then that is the point which kind of represents the fixed point knowledge about that loop, and that's what we actually represent in the static trace. That's in that sense it's a good question. Okay, good. I hope I have answered your question, Mr. or Mrs. Apurva. I don't know. It's very difficult to figure out the gender from the names for our names sometimes. Okay. Okay, so let me go ahead. So there are, so in order to kind of represent this entire thing, I'll come to that later, Mr. Sairaj. Yeah, so with the program analysis ontology has various concepts like what is the variable state, what is the program path, and then a program path is a sequence of conditions. So we use RDF list predicates like first, rest, nil in order to represent this. So it will become clear when I show you a picture actually. Okay. And then, so there are kind of various properties. I think this will become clear. So like, for example, the scalar variable is linked to the state information using a object property has variable state, like that. Okay. And the state information itself consists of state value and state relation. So all of these things I'll show you in a picture that will make it very clear. So here is a picture. This is a big picture. Let's go through this carefully. So this will clear a lot of doubts about how exactly the state information is represented. Now, this is a graph. So each edge is actually a triple here. Each edge is a triple. Okay. So this entire thing is a bunch of triples. So what this thing is showing is the state information of variables T and IP1 after the line 15 in the program path 4 through 11 through 15. That means the condition is true. Okay. Only when the condition is true, we will come inside this, right? Okay. So that's what this whole thing is about. So for example, if you go a little deeper into this now, so there are dummy nodes like state 1, state 2. So this is the state information about the variable T. So this is, here is T and here is IP1. So there are two boxes here. One box is for IP1, one box for T. So T is the variable. So it's abstractly represented like this. And so this abstract entity has name T and it has this variable state called, and that state also is represented in an abstractly like this with a dummy variable. And then what it has is that its value is unknown. Its value is unknown, and its the relation, of course, is equal to unknown. And here also P1 also is unfortunately unknown at this point of time. If you had taken C, for example, value would be 4. But anyway, it's no. But what is the most interesting thing is that what is the program point at which this is this state information is valid. So this program point is actually represented by a list. So in this list, of course, there is only one element because there is only one condition that we have encountered so far. So that condition is what is represented here. That condition is is true. is assumed value is true, and the condition actual condition is this file this line number 11 condition. So this line number 11 condition assumed value is true. So that is the program path that kind of tells us as to how we get into line 15. And when we get to line 15, here is the state information about T about IP1. So in general, for all the variables that are available within the scope, so we are going to have all the state information at every program point in the program. So this graph is a small snippet we have shown, but in practice, for even it's going to be a huge set of edges. Okay. But anyway, we don't need to really bother about the number of triples in this in the knowledge base, because we are going to represent it on the machine. And they are all going to be automatically generated by our programs. Okay. So is that clear? I mean, I want to proceed further. I think there have been some questions. Let me take that questions.
Oh, sir, can you listen to me?
Can we zoom in a little bit? Oh, okay. Let me try. That's a good question. So let me try. Let me try whether I can zoom in. Oops. I think, so can you see this thing now? Is it better now?
Yes,
Yeah,
sir.
1 second. I think I lost that slide. Yeah, so let me show this slide. Show this picture. Okay, is this picture better now? So if you want, I can explain this again. So basically, this is the variable. These are the variables, and these variables, the state of these variables we are representing, and we are representing this at a particular program point. The program point itself has a particular path, okay, through which we have reached that program point. The path is a list in general, but in this list we have only one node. So that node is this first node, which says this condition is assumed to be true. The remaining things are all nil. The rest of it is nil. So like that. So you can ignore these other type things, because those are more like it just says that this node 1 is a program path in our program analysis ontology. Okay. So let me see if there are questions on this. Okay. Okay, so what it kind of suffices to say now is that we're able to, let me zoom in a little bit. Yeah, is this better? You're able to see the whole slide now, or is it only part of the slide? I want some feedback. Are you able to see the whole slide?
Yeah, whole slide, sir. We can see.
Whole slide.
Yes, sir.
Okay, fine. Thank you.
Screens are seen.
Okay, so fine. Yeah. Okay. I think it becomes a little difficult for me to see both of you because it's a bigger window. Okay, so now let me proceed. Now, in general, so this is the, at this point of time, what we have is that we have collected knowledge about the particular C program. We have collected its control flow graph. We also collected what are the various pieces of information that we know about all the variables during a static trace. So all this is now in our knowledge base. Now let's come to specifying the analysis itself. So how do we specify the analysis? Now here is another very nice thing that we have done, that we are able to use RDF or knowledge graph in order to specify the analysis also. Okay. So for specifying the analysis also, we have concepts in our ontology. Okay, so but to give you an intuition about what kind of analysis are trickier than other kinds of analysis, let me imagine that we have kind of somehow load up this control flow graph as a kind of a large tree. So at every branch, we are taking either this statement or this branch or that branch. So because we are only doing a static analysis, we are going to represent both branches. So like this, you can imagine that there's a whole a big tree. So the kind of things that we would like to do is, we want to say, for example, if you are doing an analysis where you want to check whether there is a divide by zero error in your program. Okay, so that means you want to actually figure out what are all those statements where an expression is used which is having an operator like a divide, okay, and the divisor is a zero. So you want to be able to kind of specify that I'm looking for expressions of this kind, and then want to do some check there. Okay. So in general, what it means is that this entire information about the program is now available as a huge knowledge graph. So what we are going to, what we need is a mechanism where we can actually, be able to pinpoint certain locations in the graph which are of interest to us, and then say that you do something there, or you do some analysis there. So that kind of intuition is what is required in order to kind of understand the specification of the analysis. So let me show you this one. So the let's not bother too much about the abstract way of specifying this analysis, because that has other details like that. So we are actually using a language called Sparkle in order to specify these locations in the knowledge graph where we want to do certain things. So I don't know whether anybody has talked to you about Sparkle, but Sparkle is a query language for knowledge graphs. So basically what each of these expressions does is to kind of identify those program points where checks need to be implemented, and also identify the associated program variables around that particular point. So let's ignore this thing. I will explain this when we, with the help of an example. Okay. So let me proceed further. Okay. Now, how am I doing on time? I think I have time till about 11:30, right? Yeah, Mr. Tiwari, you are using what other kind of query languages? Yes, there are other query languages also that can be used. Generally, graph query languages can probably be used, but Sparkle is a W3C standard that is used for knowledge graphs. Okay.
And sir, what about the cipher queries?
Sorry?
Are they cipher queries?
Cipher. That's another language for graph query language.
Okay. So it is applicable only for the graph query.
Yeah, it is. It can be used even in this context. You can use actually. Yeah.
The syntax is actually very easy for cipher rather than Sparkle, as I.
Yeah, it could be the case. It could be the case, but then for RDF, Sparkle is the recommended.
Yeah.
Yes.
Thank you, sir.
Yeah.
Professor PSK, this is Asha here. Can you hear me?
Oh, hi. Hello. Yeah. Nice to know that you are in the talk. Yeah.
Yes. Prof, can I answer her question on cipher?
Yeah, sure. Go ahead.
Yeah. So I'm not getting your name. See, cipher queries are particularly used for Neo4j graphs. And it is used for graph databases. Now the problem is, you can store your graphs either in graph data store or you can store in triple store. So here we are talking about triple stores like Virtuoso or somewhere where query languages like Sparkle are used, and these are industry standard. But for graph stores, there is no industry standard. So every organization that comes up with a graph store has his or her own, have their own proprietary graph query languages. So Cipher is the proprietary language for Neo4j. Tinkerpop is a proprietary language for for Amazon's Neptune DB, like that. So graph databases will have their own proprietary graph query languages.
Thank you, Professor. Nice.
Thank you, Asha. So the issue of standardization is very important. So if you use a query language which is not standard, then your applications will become stuck to that, and so there's a lot of issues, right? So Sparkle is a recommended thing because it's a standard query language. Okay. Yeah. Anyway, so good. So what we do here is to kind of use Sparkle in order to locate those portions in the graph where certain analysis has to be done. So to drive the point, I'm giving you here as an example, the example here. So this is the these are the set of triples that will specify an analysis called the divide by zero analysis. Okay. So let's first focus on the Sparkle query here. I will take this opportunity to kind of slightly explain to you Sparkle also. So this is almost very similar to SQL. So it has a select, and then where is a will consist of a lot of what are called triple patterns. So each of these line is a triple pattern. So this will apply. This will select all those patterns that have type in it, and then bind the head of it to this and the tail of this to this variable. So that kind of thing is what it will do. So if you carefully examine this set of patterns that are specified here, and there is also a filter condition on top of this. So you have to ensure that these assignments that are done to these variables, that the names with a question mark are variables actually here in this particular query. So so those assignments that you do for these variables must also honor this other condition which is given in the filter. So what we are looking for is that this operator that we are looking for should be either a division operator or a mod operator, or so this is the or value. So either a division operator or a mod operator, and the expression that we are looking for is a C expression statement or a variable declaration or a return statement. In any of these places, it's possible for us to put a small arithmetic expression, right? So these are the expression types that we are looking for. So in these expression types, so is there a sub expression? So what is this query is asking? Is there a sub expression in that expressions, okay, whose right hand side operator is this divisor, and the operator itself is either the division operator or a mod operator. So sub expression is of type some operator, and that operator is a division operator or a mod operator, and the right hand operand for that is this divisor. Okay. So what is the type of the divisor? So this is the various pieces of information that this particular Sparkle query is trying to gather at that particular. So it's going to, so you can imagine this, that there is a bunch of conditions. So this bunch of conditions will actually match the graph where there is a statement or some declaration or written statement or whatever, which is using an expression which involves a either a division operator or a mod operator. Okay, and then we want to find out what is the divisor there. Okay, so it is going to finally give out the expression and the divisor and the divisor type. So these are the various things it is going to return in some sense. So so in general, there can be several points in the graph which are satisfying this conditions. That means all those places where the expression of this kind is being used, I want to check the divisor. So this, you are able to specify a whole bunch of checks at a one point by doing a Sparkle query like this. Okay, so this query is embedded in our specification. So that specification basically says that, okay, you get the results of this query and then check whether the value is equal to 0. Okay, so the left hand side is the results of that query. The right hand side is equal to 0 is what it is going to say. Okay. So I hope you get a general idea about what these specifications can be. So, so with this, let me proceed to give you a little bit now overview of this entire system. Okay, so this Opal system is pretty elaborate. So this whole thing has been implemented in our labs, and then we have interesting results about this whole thing. Okay, so let us now look at the various components in this particular thing. It also kind of illustrates the capabilities of the entire system. Now we are using Pato, the system developed by these various authors, Java and others in 2016. So, and then we extract the program triples from that. So C program, and that's represented as an RDF. Now that whole thing is fed into this box. Then what we do is we take the so this entire thing that is there in this red box is this Opal system. So the Opal system generates control flow information. So that control flow triples using the program analysis ontology are also fed into this thing. So now we have a bunch of triples, program plus control flow triples, and this entire thing is fed to a propagate agent. So what this propagate agent basically does is to actually carry out this entire static analysis. Okay, this trace analysis, generate the static trace. So that's what we call as the semantic triples, right? So these are the inferred triples. So these are the triples that we get after doing the static trace. So this I have already explained in the few slides before as to how exactly we're going to do the static trace. I even basically we are saying that we will generate the state information and all that. So this propagate agent is the one that is going to generate this. So where does it get the knowledge to do that? Is again the program analysis ontology has a bunch of rules where this knowledge is embedded as to how to analyze each of these statements of the C language and then extract semantic information from that. So there's a bunch of rules. So this is actually heart of the system in some sense. So there's a bunch of knowledge rules that will capture the knowledge about. So this knowledge is also part of the overall ontology. So the program analysis, the propagate agent basically makes use of these rules and then in some sense propagates the information that it knows about one set of the set of variables from one statement to another statement. That's why we call it as a propagate agent. Okay, so now that gives us static trace. So this the control flow graph, the static trace, all of them are fed into one place. That's called the consolidated program triples. Okay, and that consolidated program triples also has additional information, like for example, knowledge about library functions that you may be using. Okay, so this is completely outside the so we can't generate them automatically from the program. So we assume that this kind of knowledge will be fed into the system. The interesting thing about this framework is that it is able to accept external knowledge as well. Okay, so we accept external knowledge, and then it will be kind of directly put into this. It will be of course used in our propagate agent, and then that knowledge also comes into here. So now that we have a whole bunch of knowledge, we also may have to kind of check its sanity before we actually use it. So we use OWL reasoner, and for that we have a a bunch of axioms that are part of this program analysis ontology, using which the OWL reasoner will be able to check whether this entire thing is sane or not, and is it safe to use this and things like that. So after this validity checking is done, we are now able to feed it to what is called a check agent. So this is the check agent is the one that actually takes any specific analysis that you want to do. For example, this divide by zero, divide by zero analysis, or things like that, or canonical loop analysis, or whatever kind of points to analysis, etc. So that analysis specification can also be specified in our program analysis ontology using RDF. So that it will take as the input the check agent, and then actually it will generate. So there are actually various things that the check agent does. For certain kinds of things, the check agent can actually simply run certain Sparkle queries and then carry out this specification and then give you output. Okay. Whereas for certain kinds of things, it will have to use what is called a constraint solver. So SMT solver is a constraint solver. So in such a kind of analysis, what it will do is to generate a bunch of constraints that if they are fed into an SMT solver and solved, then that is going to give us an output of the analysis. So I'm going to illustrate that with the help of an example in a short while now. Okay. So I hope you get an overall picture of this particular interesting kind of system. Are there any questions now at this stage on this diagram? Okay, so let me proceed then. So this is the information that I already said. So the program, the propagate agent actually generates the static trace tuples and then represents them using the program analysis ontology. So let me give you an example of well, how exactly it does this. So as I have already pointed out, the kind of the method that we have to use in order to generate this static trace is that you have to explore every program path in each of these functions, and then process each of these statements using a bunch of rules, and then generate these state information. Okay, the static trace triples. Okay, so to give you an idea, this is a simple kind of a rule. So for a if statement, so there will be a rule which says that whenever you encounter an if statement, you generate this kind of static trace triples. That means, see, for the variable x here, after the statement s1, so you let's say you have reached this particular path using a program path called p1. So for this p1, now we add that c1 is true, because if c1 is true, only x1 gets executed, otherwise s2 gets executed. So then the value of x will be equal to 2. So that kind of analysis it's able to do, and this analysis is being done with the help of a rule. That's what the whole idea is about. Okay, so we actually did not write the rule itself here, but we are telling as to what will the rule do. Okay, I hope it's clear. Yeah. So with so there's a whole bunch of rules like that in order to handle various kinds of C statements that are possible, and including loops and things like that. So with the help of those rules, the propagate agent will generate lots of this static trace triples. Then the check agent, as I was mentioning, implements the actual analysis specification. Okay, so recall that in the analysis specification, we may sometimes have Sparkle queries. So what it does is to take those Sparkle queries, execute them, obtain all those program points where the analysis has to be performed, and then take the values and constraints, all those variables at those program points, pick up the values constraints on those variables, and then generate these constraints called the SMT constraints, so that when they are fed into an SMT solver, we will actually be able to figure out whether what we are looking for is happening there or not. So to kind of so the constraint satisfaction, we actually use what is called Z3 solver, which is a state-of-the-art SMT solver. So here is an example. So in the same example, let's say we want to do divides by zero check. Are all the division operations safe or not? So the division operation is actually happening here. the division operation is happening here. 1024 divided by IP1 minus T. So I will not go into the details, but anyway, what the check agent does is to generate all these various constraints. Okay, these constraints are like, for example, IP1 minus T equals 0. So this is the divisor. So the divisor should be 0. If that is the case, then we are in trouble. Okay, so that's what we want to check. So this is part of the analysis specification. So check whether the divisors are 0 or not. So from the analysis specification itself, it will figure out that this is the place where division is being done, and this is the right hand operator for that, and this is to be equated to 0. So it will figure that out. Okay, and then put that, and then the trace of the program has given a lot of information about the variables that it has in the scope of this particular statement. So all that variables also are given. For example, if you know that IP1 is much greater than T, then IP1 minus T will be positive, and there won't be any divide by 0 issue. But unfortunately, at this stage, having done this analysis, we figure out that we don't know anything about IP1, we don't know anything about T. So both of them are unknown, and so because it is quite possible that they may be equal, and so it will become 0, and that's where the potential bug exists at this particular line. So the whole system will be actually point out the line where this kind of a problem occurs. Okay, so so this is an example of a divide by 0 kind of analysis that can be carried out with the help of this entire infrastructure. Okay, so I hope the overall set of concepts that I'm talking to you is generally clear, I hope. So if you have any questions, I will take them, because now I think I have more information about the performance of the whole system, which is be little not very important for this audience actually. I'll probably stop here and just show you some of the pictures actually. So we tried doing this whole thing. We have tested this entire system on industry standard benchmarks. So there are what are called spec benchmarks for doing this. Say for example, stream safety analysis. That means whether the function, the files are handled properly or not. So with these benchmarks, we have tried these things. So there are two components to the whole system, right? The propagate agent and the check agent. So the propagate agent actually runs only once, because it is generating the static trace only once, and it puts this whole information into a knowledge base. Once it runs and generates the knowledge base becomes reusable for a series of analyses. Okay, so I'll show you that. So the check agent, so when we compare it with the Clang, the check agent is taking about half the time of the Clang, but then the check agent and propagate agent together have to be taken into consideration. Anyway, so the performance is comparable. So that will be the summary, but the performance is not is one of the not the major focuses here. But the whole ability to kind of use this knowledge bases within the domain of program analysis is what is the most important contribution here. Okay, so here for the divide by 0 analysis, we're able to do much faster. Opal's check agent will do much faster, because basically it is making use of the knowledge base that has been generated by the propagate agent. Okay. So in order to show you more the advantages of having a knowledge base, so let's consider a series of analysis. I will not go into these things. You can probably take it up later. So basically what it says is that there are a bunch of 8 kind of analysis, all related to files, which can all be done one after the other. Okay. If you do them one after the other, even if you do them one after the other in a Clang kind of atmosphere, where there is no passing of knowledge from one analysis to another analysis, they'll have to do everything from the scratch. Whereas because we are able to use a propagate agent and then construct a knowledge base about this whole program, we're able to do this kind of analysis, in a much faster manner. So you can see that here in the picture. So the blue line is this opal picture. So if you do a series of analysis and then plot the cumulative time that you take, it rises slowly here. Whereas for Clang, it's always increasing like that. So that's because they don't reuse anything. They don't construct a knowledge base at all. Anyway, so this is the story about this whole thing. And of course, there is also a lot of gains on the programmer productivity, because these opal specifications for various kind of analysis can be very compactly specified with the help of Sparkle queries and all that. Whereas they even in declarative style like Pato, they need a lot of these lines of code to specify, say for example, canonical loop. So notice that Pato cannot do stream safety and divide by zero kind of analysis, because these require detailed static trace information. We're able to do that, and we're able to do it in much faster, specification wise it's much faster and easier to specify compared to the traditional ways of doing it. Anyway, so let me pause here, and then actually this, I think we have come to a conclusion. So let me take questions here as you are reading the conclusions. So even though I started 5 minutes late, 7 minutes late, I am able to complete it on time, Dr. Sarika.
Yes, sir. Definitely.
So let me take questions now. I think let me open the chat box. What other? Okay, this is the stuff that we have already answered. So not only questions on this, I mean, any other discussion points, that you may want to, remarks you may want to share, you are welcome to do that. In the last minute, I had to, come from home to office, exactly 10 minutes before 10. I had to rush from home to office because the home had no internet connection. Otherwise, we have been operating from homes. And office, there's a lot of construction going around in this place. I'm sorry for the background noise. We can't help that. Anyway, so it's a nice session. Nice to have interacted with all of you.
Did you get the background
Sir,
noise?
sir, can I ask you a question?
Yeah, sure. Go ahead, Sairaj.
Sir, there is one language called semantic web reasoning language, and the other thing is SparkQL. How both are different, sir? May I know the difference between them in case of implementation?
One second. One of them is Sparkle. The other one is
SWRL.
okay.
Semantic
Semantic
web.
web rule language. Yeah. Okay. See, I will put this in very simple like this. Sparkle is a graph query language. So knowledge graph. So you can query the knowledge graph and then use make use of the Sparkle to kind of specify the patterns where a certain pattern subgraph has to match the graph, and then you can pick up information from there. Okay. Whereas using semantic web rule language, it's possible for us to kind of alter the graph, saying that if this pattern exists in the graph, you go and add this edge in the graph. So that kind of updates you can do in SWRL. It's a rule language using which you can actually add additional edges in the knowledge graph. To put it very bluntly, simply. But if you go into the detail, you'll figure out that. Thank you. Yeah, a nice question. Yeah, I hope it answers your question.
Yes, sir.
Yeah.
If you other participants saying sorry, also created here.
Dr. Sarika, your voice is not audible properly. There's some issue.
Yes, sir. I'm also looking at it.
Yeah.
Sir, this is Praveen, sir.
Yes, tell me. Mr. Praveen.
Sir, we have these sequential models like RNNs and okay, so this kind of artificial neural network, sir.
Yeah.
So they always say that when we are going to capture the semantics, okay, so by reading from left to right and right to left and sentence level, character level, like this, they are saying.
Right. These are various machine learning models. So we are not dealing with machine learning. Yeah.
How this, okay, so ontology is okay, so differing with this kind of thing. So why again, okay, so this ontology we have to build by training a lot of this kind of
Yeah,
things.
there's some background noise. Dr. Shanta or somebody. Sharmila, Dr. Sharmila, can you please mute your audio? Yeah, thank you. Yeah, so Praveen, so to answer your question, these are complementary approaches. Machine learning and knowledge bases are complementary approaches. One cannot do the other kinds of work actually. So machine learning is applicable in certain contexts, whereas knowledge bases are kind of applicable in other kind of contexts. For example, we are actually now, this kind of very precise analysis that involves a lot of knowledge. I don't think can be actually carried out by machine learning approaches.
Sir, for example, sir, in my area, okay, so I am working on analyzing the poetry, sir, American poetry and Indian poetry kind of thing.
I see.
So for this one, okay, so I was working with these sequential models to analyze and to classify these two categories. So for this one, okay, so this ontology is a specific one, or is it going to be good one for this kind of thing? Okay, domain kind of thing.
I think so. So in your domain, I mean, it's a very interesting domain you're talking about. Suddenly you're bringing in poetry, but you see, a poet understands a poem, and then kind of figures out what are the various elements in it and what are the various kind of features that it uses and things like that. So he understands it with a lot of background knowledge, and he extracts pieces of knowledge from there, and then analyzes two different kinds of poems, and then figures out their characteristics or comparisons or something like that. If you're one thing is you can use some components that are based on machine learning, in order to extract pieces from the data and then represent that into ontology. That's also possible.
Okay, so get the representations from that one and represent as a knowledge base kind of thing.
Right.
I see.
Yeah.
Okay, thank you, sir. Thank you.
Actually, now that for the future of AI is actually trying to combine the two approaches of using knowledge bases as well as machine learning based approaches in order to further we're kind of moving towards what is called explainable AI and all that.
I see, sir. Okay. Thank you, sir.
Yeah.
Sir.
Yeah.
I'm Sairaj again, sir.
Yeah. Tell me.
Sir, in relevance to the previous question asked by Mr. Praveen, I want to ask one question, sir.
Right, go ahead.
In recent papers, I have found an architecture called neural Turing machines. Will that support these state transitions, and can I capture the knowledge from the text using that, so that ontological analysis will be better?
I have no idea about that actually. So you are talking about something which I don't have much idea about. Neural what?
Neural Turing machines, sir.
Neural Turing machines. Okay, I see. I don't know much about them, so I have not read about them. So I can't comment much. But there have been okay. In general, you can think about it as some kind of an approach where there's a trying to combine the efforts of neural networks with trying to represent them into a knowledge graph kind of a thing. I don't know. Maybe, yeah. So, but it all depends on the problem at hand that you have, and maybe it'll work. I don't know. I have no idea about those. new kind of models that you're talking about. Yeah.
Okay, sir.
Yeah.
Okay, sir. Thank you, sir.
Yeah. Okay. So good. Are there any further comments, questions that you have? I now find that if you want more technical details and all that, my student Dilip is also attending the talk. I don't know whether um, he is still there.
Sir, I'm available, sir.
Oh, very good, Dilip. Thank you. So we can take more detailed questions also. You can always write to us about if you want more. You're audible feebly. Yeah.
Okay, now a bit better. Okay,
Yeah.
actually, there are no more very technical questions. The reason being, all the participants are new to this field. Only
Yeah, I know. I expect that.
Know the field from beginning only.
Yeah, I know that. So actually, they're new to semantic technologies. They're also probably new to program analysis, and now I'm combining both of them. So it's obviously very. So I don't expect all the people to kind of even 100% understand what I'm saying. Also, it's okay. It doesn't matter as long as they get the overall idea of the field and the power of ontologies to do various things. I think the session has served the purpose. Yeah. Thank you. Yeah.
You would that they got an idea how to use, how to apply ontologies in program analysis.
Yeah.
In that session, they will do it for mechanical engineering itself.
Yeah. Sorry?
But in the next lecture, it is Dr. Kanham Pani Kumar.
Oh, yeah. True. Yeah.
Mechanical.
Yeah. Right. I think it's going to start in a few minutes, right? Yeah. So I should probably stop here now. Thank you all for your participation. I'm going to stop presenting and.
Thank you so much, sir. We are fortunate enough to have you here. And yes, the students, the participants had an idea of how to apply ontologies at various different places.
Thank you. Thank you, Dr. Sarika.
If the participants wish to switch on the video, then we can definitely take certain screenshots.
Oh, you want to take a screenshot? Okay.
If the participants are in video mode, it is always good.
Dilip, you want to switch on your video?
Okay, this is the Kumar, your student. Dilip, where are you now?
Sorry? You're asking who?
Where is Dilip now?
Dilip is at his home residence.
No. He's affiliated to.
Oh, he's yet to submit his thesis.
Submit the thesis, okay.
Yeah.
So he's with you right now.
Yeah, he's still my He's in a CS department. He is planning to write his thesis and submit it in about 6 months' time or something like that.
Okay. Fine. That is so good. Okay then. Thank you so much.
Thank you. Yeah.
Thank you everybody. And,
Thank you. Thank you,
join,
Dilip, for joining.
join the next session. Sir, it will be so nice if you join us the next session. Join with us the next session. And I can see you were there with us since the day one. That is very motivating for all of us.
Okay.
Thank you so much, sir.
Thank you. I have to leave now because I have a class at 1 o'clock. Yeah.
Okay, sir.
I may not be able to, join Pani's talk, but yeah.
Abhishek, let us see here only. I think that will be better because it is just 2 minutes. All of us will go there. So why not you bring all those people here? We are 92 here.
Okay, ma'am. Actually, sir is there. So should I call him here?
You can bring him here. There is no problem. He will understand.
Okay, ma'am.
Because we are 91 here. All of us will go there. There will be a problem.
Okay.
So the participants can have a break, can take water, can take tea, and within 2 to 3 minutes we'll be starting. because the expert has already joined us. Can somebody tell me, am I better audible from previous or the same problem persists?
Ma'am, I have asked sir to join this link.
Okay. Are
He's
there
coming
other
here.
participants also?
Yes, ma'am. I have dropped a message also.
Now you have to drop a message on WhatsApp group also.
Okay, ma'am. Let me know.
Just like afternoon session and write this meeting.
Okay.
Dr. Senthil, we will be here only. Veera Kumar. It's Veera Kumar who is asking whether the link is same or we have to switch. Let us be here on this link only. Do not switch, please. But 10 of the participants are already gone. So it's 83 now. Dr. Gandham Pani Kumar has already joined us.
Good morning, ma'am. Fani Kumar here. Are you able to hear?